Hey everyone, welcome back to the Mindverse. Today we are diving into a topic that sounds simple at first, but is actually one of the deepest and most mysterious forces shaping our entire universe. We're talking about gravity in space, and why it's not what you think. When most of us hear the word gravity, we picture being pulled down toward the Earth. It's what keeps our feet on the ground, what makes objects fall when we drop them, and what keeps the moon circling around us. But once we step outside the familiar comfort of Earth and begin to think about space, gravity reveals itself as something far stranger, more powerful, and more mysterious than the everyday pull we feel here on the surface. By the end of this journey, you'll see gravity in a way you may never have imagined before. Let's start with a common misconception. Many people think that in space there is no gravity at all. They look at astronauts floating inside the International Space Station and assume they are in zero gravity. But the truth is, gravity never disappears. The International Space Station orbits Earth at a height of about 400 kilometers. And at that altitude, gravity is still around 90% as strong as it is on the surface. If you weighed 100 kilograms on Earth, you'd still feel around 90 kilograms of pull there. So why do astronauts float? The answer is that both they and the station are in constant freefall. They are falling toward Earth all the time. But because the station is moving forward so quickly, it keeps missing the planet. That endless fall is what we call orbit. Astronauts float not because there is no gravity, but because they are caught in gravity's embrace, falling forever around our world. Now let's step back and look at Earth itself. Our planet is not sitting still. It's racing around the sun at about 100,000 kilometers per hour. The only reason we don't fly off into space is because the sun's gravity bends Earth's path into a nearly circular orbit. Without that constant pull, Earth would shoot straight out into the galaxy and life as we know it would never exist. Every other planet in the solar system is caught in the same dance, orbiting the sun because of gravity. Even Pluto, so far away that sunlight takes hours to reach it, still feels the faint but steady grip of our star. Gravity's influence stretches that far, but gravity's reach goes far beyond the solar system. Our galaxy, the Milky Way, is made up of hundreds of billions of stars, and all of them are bound together by gravity. It's the glue that holds the spiral arms in place and keeps the galaxy from flying apart. Yet when astronomers calculated the amount of visible matter in galaxies, they discovered a problem. The stars, gas, and dust we can see are not enough to explain the strength of the gravity that holds everything together. There had to be something else, something invisible, adding its pull. That mysterious something is what we now call dark matter. We don't know exactly what it is, but we know it's there, and we know it outweighs normal matter many times over. Gravity exposes its hidden hand. All of this shows that gravity is not just about pulling things downward. It is the architect of the cosmos, shaping galaxies, sculpting solar systems, and even guiding the fates of stars themselves. And our understanding of it changed forever when Albert Einstein came along. For centuries, Isaac Newton's idea of gravity as a force between masses explained things beautifully. But Einstein asked a deeper question. What if gravity is not actually a force at all? What if it is the bending of space and time itself? According to his general theory of relativity, massive objects like planets and stars warp the very fabric of reality, and smaller objects simply move along those curves. Imagine placing a heavy bowling ball on a trampoline. The fabric bends inward. Now roll a marble across the surface, and it spirals inward, not because the bowling ball is pulling it directly, but because the surface itself is curved. That's how Earth orbits the sun. It's not being pulled by a mysterious force. It's following the shape of the curved space-time around the sun. This way of thinking explains not only planetary motion but also some of the most extreme objects in the universe. Black holes. A black hole forms when a massive star collapses under its own weight. So much mass is packed into such a tiny volume that space-time caves in, creating a region where gravity is so intense that not even light can escape. Black holes are not just science fiction monsters. They are real, and they shaped galaxies by swallowing matter, bending light, and even merging with one another in violent cosmic collisions. When black holes collide, they create one of the most extraordinary phenomena ever detected: gravitational waves. Gravitational waves are ripples in space-time itself, like waves spreading across the surface of a pond after you drop a stone. Einstein predicted them a century ago, but they were only confirmed in 2015, when detectors on Earth picked up the faint tremors of two black holes merging over 1 billion light-years away. Think about that. We can now listen to the universe through the vibrations of gravity itself. That discovery opened an entirely new window on the cosmos. So if gravity is everywhere and so powerful, how do spacecraft escape Earth? The trick is speed and distance. Gravity follows the inverse square law, which means the farther away you are from an object, the weaker its pull becomes. Double the distance, and gravity's strength drops to a quarter. Rockets work by pushing hard enough to overcome Earth's gravity, but once in space, spacecraft can actually use gravity as a tool. By flying close to planets and using their gravity to slingshot forward, spacecraft can gain incredible speed without burning extra fuel. This clever trick, called a gravity assist, allowed the Voyager missions to travel to the outer planets and beyond. Gravity becomes both an obstacle and an ally in our exploration of the stars. But gravity doesn't just shape spacecraft, it also affects humans. Our bodies evolved under Earth's steady pull, and when we leave it behind, strange things happen. In microgravity environments like the ISS, astronauts lose muscle mass and bone density. Fluids shift upward in the body, vision can be affected, and even the heart changes shape. Long-term space missions will need solutions to these problems, whether through exercise, medicine, or even artificial gravity. Without gravity, the human body struggles to stay healthy. Gravity also decides the fate of worlds. Jupiter, with its enormous mass, acts as a kind of cosmic protector for Earth. Its gravity pulls in or deflects many comets and asteroids that might otherwise hit our planet. Without Jupiter, Earth might have been struck so often that life could never have developed. On the other hand, Mars, with its weaker gravity, could not hold on to its thick atmosphere. Over time, the air thinned and the planet became cold and barren. Gravity shapes whether planets are protective havens or hostile wastelands. Now imagine the universe without gravity. Stars would never ignite, planets would never form, galaxies would never gather together. There would be no structure, no warmth, and no life. Gravity is the silent architect of everything we see in the night sky. It builds, it binds, and it holds together the grand stage on which the universe unfolds. And yet, for all we know, gravity remains one of the greatest mysteries in science. We can describe how it works, but not why it exists in the first place. Why does mass bend space-time? Why does a universe follow this rule? On the scale of atoms and particles, gravity seems almost irrelevant compared to the other forces of nature. A tiny magnet can easily overpower Earth's entire gravitational pull on a paperclip. And yet on cosmic scales, gravity dominates everything. Reconciling these two pictures, quantum mechanics on the small scale and relativity on the large, is one of the greatest challenges in physics. If scientists can unify them, we may finally unlock the ultimate secrets of the cosmos. So the next time you see an astronaut floating in orbit, remember that gravity is not gone. It is the very reason they are floating, the invisible hand guiding their fall around Earth. The next time you look up at the stars, remember that every one of them is held together by gravity, burning brightly only because gravity keeps their nuclear fires alive. Every planet, every moon, every galaxy is part of this cosmic dance choreographed by an unseen force. Gravity in space is not what most people think. It is not just about falling apples or keeping us stuck to the ground. It is about the birth of stars, the paths of planets, the swirling arms of galaxies, and the bending of space and time itself. It is about black holes that trap light, waves that ripple across the universe, and mysteries still waiting to be solved. It is both the most familiar and the most mysterious force we know, and it is far stranger, far deeper, and far more powerful than we can ever fully imagine.